All right, great. Thank you so much for joining, everybody. First of all, happy World Quantum Day to all of you. So I'm so glad that we're able to do this today. So today's Q Industry session is special because unlike the usual format, we're going to have a panel discussion. And we've got five extremely esteemed individuals joining us today. So let me start by introducing them. First, we have Devika, who is a mathematician. She did her PhD in number theory from TIFR Mumbai, and she currently heads the quantum error correction team at Quantum Source, which is an Israeli startup which focuses on building a photonic quantum computer. She is also a silver medalist from IIT Bombay, and which is where she did her master's in mathematics. Before this job, she was a postdoc at Weizmann Institute, where she switched from math to computer science. So welcome, Devika, and thank you so much for joining us. Also, I have to say, Devika has been instrumental in the planning and execution of this session. So thank you so much for that. Devika. Then we also have Achintya Paradkar, who is a doctoral candidate at Chalmers University in Sweden. And his research is in the field of quantum sensing using superconducting circuits, which is what he'll be talking to us about today. And his work involves bringing a magnetically levitated microparticle into a macroscopic quantum state with the aim to test the limits of quantum mechanics. I'm hoping he'll also tell us a little more about that today. And he did his master's in nanoscience and nanotechnology at KU in Belgium, and also his bachelor's in mechanical engineering from Pune University. So that's Achintya. Thank you so much for being here, Achintya. Welcome to you. Next, we have Kishor Bharti, who is currently serving as the quantum machine learning domain head at the Institute of High Performance Computing, which is hosted by A-Star Singapore. Before this, he was a postdoc at the Joint Quantum Institute, the Joint Center for Quantum Information and Computer Science, and the National Institute of Standards and Technology NIST in Maryland, USA. In 2021, he earned his doctoral degree from the Center of Quantum Technologies, and his research primarily focuses on a diverse array of quantum physics, which includes quantum device certification, near-term quantum computing, quantum foundations, QML, quantum error correction, and so on. So he is a referee for leading academic journals and conferences like Nature Physics and QIP, and he also handles grant applications. Kishore is also an editor at the journal Quantum. Thank you so much again, Kishore, for agreeing to be a part of this session. We're hoping to hear more about his algorithms and computational advantage in the near term from you. So yeah, that's Kishore. We then Anuj, who's been a part of Q India for a while now, and I'm sure a lot of us know him. He is an emerging technology evangelist with excellence in digital transformation, cloud architecture and governance, and quantum computing. He is a mentor at QOSF and also an IBM Qiskit advocate. He is also associated with the IEEE Quantum and Consumer Technology Technicals Committee. So the work he does now focuses on enabling other organizations to adopt quantum and emerging technologies by helping them in strategic planning, identification of business use cases, conducting proof of concepts, and all of these mainly in the manufacturing and finance domain. So today, Anuj will bring in the India perspective to this conversation, and he will give us some insight into where India is, especially in the context of the recent quantum communication conclave that happened at the end of last month in Delhi. So thank you so much, Anuj. Anuj has also helped put this session together. So we're really glad that he's also a panelist today. Finally, we have Rajiv. I don't think Rajiv needs much introduction in this particular group, but he's a quantum algorithms researcher. For the last 3 years, he worked as the head of the R&D division at Goldman Sachs, and his work involved understanding quantum-enhanced Monte Carlo methods and quantum arithmetic for financial problems. He was, before that, he was a data scientist in the global markets division at Goldman Sachs at the foreign exchange desk, and as a postdoctoral fellow in quantum technologies in a joint appointment with the AT&T Foundry and Caltech. So Rajiv completed his PhD in 2018 in experimental atomic physics at Stanford University, where he worked on creating highly entangled states for quantum sensor applications. Today, Rajiv will be bringing to the conversation nuances of funding, investment, and things like that. Also, Rajiv has been instrumental not just in putting this session together, but managing all of these World Quantum Day sessions that we've all been enjoying. So yeah, shout out to Rajiv. I also, just before we start, I also want to say a huge thank you to Karthikeyan, who's also here somewhere, I hope, and Ameya, who were also extremely helpful in putting this together. So yeah, thanks everybody. I think we'll get started immediately. The plan for the session is to have each panelist give us their perspectives and then have a short discussion after each panelist gives their introductory remarks. If you have any questions, please feel free to use the chat. At the end of the entire session, we will have a Q&A bit as well. So we can start it. I'd like to invite Devika first to talk to us about photonics and quantum hardware and where the industry is and what she thinks the current trends are and so on. The floor is yours, Devika.
Hi, Priya, and hi, everybody else. Thank you for such a kind introduction. It's always nice to hear other people talk about you. Okay, so I'm going to begin with also, even though she did give me credit for coming up with some ideas for this, it's entirely her hard work to put it all together. So I don't want the credit for that. Okay, so I'm going to describe what a photonic quantum computer will look like very, very roughly. So the idea is that a photon, which is a light particle, will be used as qubits. And specifically where I work, we work with dual rail qubits. So it basically means that you have two rails and you send one photon through the rail. And one of them is the zero rail and the other one is the one rail. So with some probability, it's zero, and with some other probability, it's one. And that's how it behaves like a qubit. Priya, can you mute the other there's one of the audience members that's unmuted. Oh, sorry. Yeah, unmuted. Somebody with AK, and there's background noise from them. So we will use photons as qubits and specifically as dual rail qubits. But the cool thing, the cool thing about photons is that they can travel far and wide, but they do not interact with each other. So you need a third party to entangle two photons together. And in my case, like where I work and also in most of the startups, they're using atoms to help entangle two photons, okay? The idea would be that you capture an atom, you entangle a photon with it, and then you swap out the state of the atom onto another photon. So in this way, originally a photon and an atom were entangled, and now when you've swapped out the atom onto another photon, these two photons will remain entangled, and then you can do error correction or fault tolerant computation on this. Okay, so this is the basic. This is basically what photons can do. The problem with photons, however, is that they're very short-lived. They're not like superconducting qubits, which Achintya will describe in a bit. And also the fibers that they are stored in, which are used to make them travel from one place to the other. If the fiber is too long, you can lose the photon. So photons can also be lossy. So being short-lived and lossy is like two of their biggest drawbacks. And the third party entanglement procedure is also quite delicate. So all of these things have to be really controlled. Further, photons can also be distinguishable, and this can create more errors. So these are like the four main cons for the photonic industry, but all of these cons have some solution. And all the startups are trying to focus on which solution can help figure out, get over these cons. In the pros side, like I said, photons can travel far and wide. So they're a good candidate for QED protocols. Also, because they can travel far and wide, scaling is possible because you just need the optical fiber to be as long as you want your computer to be, as big you want the computer to be. And so I've been using the word optical fibers. So these are the two hardwares that you use in a photonic setup. It's optical fibers and silicon chips. And the good thing for the photonic industry is that these two things have already been advanced because of other reasons of the advancement in the technology industry in the last 3 decades. So we have really good optical fibers already, and we also have really good silicon chips. We just need to put these two together and hope that you can keep the qubit alive in a photon and do computation with it. So these are the things on the hardware level. Theoretically as well, there are computational schemes like measurement-based quantum computing or fusion-based quantum computing, which are extremely suited to the photonic setup. They mainly overcome the fact that photons are short-lived. So you basically copy photons over, like you copy one state over several photons, and you encode it in a big space, and you use it, and you measure it, you keep measuring it out, and you keep computing it also at the same time. So at a particular time, you will only have a little strip of photons alive, a little strip of entangled photons alive, and things that you've measured out have moved on, and things that you're adding onto the entanglement can help you proceed with the computation that you want to do. Okay, with that said, the startups in this area are the main startup in this area was founded in 2016. It's called Xanadu in Canada. And that company has a full stack approach, like they're doing in-house hardware as well as software and promising to provide a state-of-the-art computer for everybody to use. The other startup, which has started coming up a lot in the news, and probably Rajiv will also talk about it, is called PsiQuantum. They're based in Palo Alto, and it's a group of really clever people, I personally think, because I follow their work very closely. And maybe Kishor have heard of them because they publish in QIP like 5 papers every time. And they are also a photonic-based quantum computing firm, and they are the ones who came up with this fusion-based quantum computation scheme. And the third startup that I want to talk about is where I work. It's called Quantum Source. The main idea is from a physicist from the Weizmann Institute here in Israel. This was founded in 2021, and we're doing pretty well. We're funding-wise and also achieving the things that we wanted to achieve in every slot. Okay, that's it. I am open to questions.
Yeah. Yeah, so that was a really nice introduction to photonics and how it works. So if I invite the other panelists, if you have any comments or questions, observations you'd like to make. Yeah, I think Anuj.
Yeah, so I just want to add up, like the way I'll be concentrating myself to the Indian ecosystem only. So I'm not talking about like how the things are developing around like in globally, but in India, also, main focus is one of like photonics. Apart from the superconducting qubit, photonics is one of the area where Indian research organization, I would say, are mainly focused on, and within the vertical itself, it is the quantum communication. which is spearheading and absorbing this particular technology. So that is there, and there is like when the opportunity comes, so I'll be actually adding few more things how this particular ecosystem is working. But this is one of the primary focus apart from superconducting or other cold atom technologies, anything else. But photonics is something on which like even India is actually focusing on having their own quantum computer.
Okay. Where in India, which organization is involved in the photonic computing?
It is mainly IIT, to be specific, IIT Madras. I think where Priya is already there.
Oh, really? Okay.
In terms of startups, of course, in India, there's a bunch of quantum communication startups, but I think Confluence is one startup that's looking at photonic qubits for quantum computing specifically. So that's the one startup that's focusing on this that I know of. But I did have one question. So you did mention what we already have in terms of hardware. So classical optics or photonics hardware and making use of that. So do you foresee that because a lot has been done in classical photonics and industry is already built on that. Just because we have that advantage of migrating, that photonics will perhaps be the most successful qubit modality?
I think I do partially agree with you, and this is also the reason why photonics is getting a lot of funding in the world right now. This is what I believe. But the fact that inherently photons can travel far and wide, it's also a very useful modality for QED protocols. And definitely the fact that hardware has already been developed already gives them a huge jump start. So yes, in short, the answer to what you asked is yes.
I have a question for Kishor, because I think, Devika, you started off with talking about dual real qubits, and recently we've heard a lot about the advancements in quantum error correction with superconducting qubits. Google had a paper come out, and then recently even Yale had another paper come out, although I don't think they were working with superconducting. So I just wondered what challenges there are with photonics when it comes to NISQ algorithms and then beyond that, quantum error correction.
So I think, the challenges, like I would say, are very much at the moment mostly like platform agnostic, like in the sense that when we talk about, NISQ algorithms. So I will discuss some of them. So there are things like, so NISQ algorithms are mostly heuristic, and there are no provable guarantees. But then the beauty of NISQ algorithms is like, similar to, you can say, the beauty of neural networks over support vector machine. That when devices mature, like if your heuristics can sometimes totally, outperform some of the well-developed mathematical models. So support vector machines, they are like, based on like, they have very nice convex optimization framework and all, but neural network, nobody understand. And using Node, we have this chat GPT and whatnot, and you see like it's already, so basically, but then the question is, your heuristic should be, for them to shine, your devices should be matured. And then on top of that, there are certain challenges, like you cannot simply take a classical model, turn it into a quantum model, and expect that everything will work fine. So there are challenges related to, like how to better train, how to better, come up with an answers, how to better understand, like the expressibility. Then, yeah, there are also like, platform dependent challenges also. So let's say when you are thinking about, like continuous variable systems, then in that case, let's say if you are interested in error correction, then you have to think about, in terms of Q modes and, so basically, like then you have to think about like, this analog quantum error correction schemes. And there are, I mean, even though initially I think people thought that, but this GKP paper came in early 2000, and people thought that, it might be difficult to realize. But then I think recently, I think a few groups have, got some good progress along this direction. So I mean, we don't know at the moment. Photonics is definitely one of the, I would say, strong candidate. Because I mean, if you look at psi quantum, they say that, they believe this is the only way to have, 5 million qubits or whatever. Because with when photons are, and the photons are, you can have many photons, and you can, there are certain challenges, but yeah, I mean, do not know, with respect to the, so with respect to near term, I mean, yeah, in the near term, you need to, I mean, it's mostly, I would say, a question of coming up with a nice algorithm with guarantee that can work in the near term. I will discuss some of the things, I think I tried to make it formal, so I prepared a small number of slides, so basically, yeah, I will discuss a bit, some of these things. So
sure, yeah, thank you so much.
Can I add one thing? Yeah. One very short thing, specifically for photonics with respect to error correction. Photons do not bit flip. Bit flip in photon is very rare. What mostly happens in photons is loss. So surface codes, it's a good error correction code, but it does not handle loss so well. So there are other ways, and we are looking into them, of how to handle loss in photon, like loss in an encoded scheme. Because bit flip in a dual rail photon it's a rare phenomena.
Okay, interesting.
That's all. Yeah.
Okay. Yeah. Okay. Thank you so much. Yeah. So I feel optimistic about photonics after what you've told me, but then I guess we need Achintya to come and tell us what he thinks, because he's going to bring in perspective of superconducting qubits. So Achintya, the floor is yours now.
Yeah, thanks, Priya. So, yeah, well, let's see. As Priya earlier mentioned, so I am an experimental physicist who works in superconducting circuits. So I do not know, my expertise do not lie in algorithms and quantum computation, but rather in the fabrication of Josephson junctions and superconducting circuits and all the various hardware challenges that are involved. So even though I do quantum sensing, I do sensing with superconducting circuits, and that is what I'll be focusing on. And alongside that, I will also throw some light on other modalities of qubits. So let's begin. Yeah. Well, when it comes to qubits, qubit realization, there are around 5 most prominent ones. So you have spin qubits, you have charge qubits, both based on electrons and various other physical realization. You have superconducting qubits, NV centers, photonic or bosonic qubits, and then you have these neutral atoms with Rydberg states. And well, there are few other, novel ideas, but these are the most prominent ones. So with regards to spin qubits, if you begin with that, that's the most simple and easy realization in conceptually speaking, because there all you have is an electron that can either have state spin up or spin down. And this is what you control. It's very intuitively easy to understand compared to, let's say, superconducting qubit. And here, the advantage that you get is, well, first thing, a spin state is a highly stable state. So you have very large T1 time. You get the lifetime of your qubit is in the order of seconds. So that gives it a very good, makes it a very promising candidate. And second advantage is that you can you can trap these electrons in a quantum dot that is made of silicon technology. So in terms of fabrication, again, you get an advantage. So this is one way of doing it. Another way, using same silicon quantum dot, you can realize this to 0 and 1 states either with a spin or alongside using a charge. So the presence or absence of an electron inside the quantum dot can also be a 0 and 1 state. And in both of these implementations, the control is fully electric. Unlike, let's say, superconducting qubits or these NV centers where you need magnetic field for controlling, here it's fully electronic. And the dimensions are in the order of nanometers. So there itself, you have a lot of advantages when it comes to scalability. And this is one of the reasons why companies like Intel are heavily investing in this direction. But then on the downside, the highest achieved entanglement in silicon qubits is only up to 3 qubits. So although it is promising, not much has been realized in this direction, although it can make a very good candidate for a qubit realization. And then it also has issues with crosstalk when you try to scale it up very large or try to miniaturize the circuits too much, because the coupling in that case is capacitive. Well, that's with regards to spin qubits. And now talking about another realization, which is superconducting qubits. So a superconducting qubit can be simply understood as an LC resonator. Most familiar with electronics know what an LC resonator is. It's basically a device that, or let's say an element that can store energy and has a resonant frequency. And then if you have two such energy levels, you can define them as 0 and 1. In case of superconducting circuit, the inductive element is made of Josephson junction, which can be tuned with a magnetic flux. So that gives you the control parameter, and then you can tune the Josephson inductance to vary your qubit frequency with a magnetic field. And another advantage is that since you're using a superconducting circuit, there is no resistive element. And then you do not have electrical losses. So all of this combined gives you a very good T1 lifetime of, let's say, around 100 microseconds, which is already good enough to begin with. And the state-of-the-art gate fidelities are in the order of 99.99% in most cases. So this is 2-qubit gate fidelity. And then since it's an LC resonator and you're using coplanar waveguides, which are very familiar in the electrical and electronics domain, designing a superconducting circuit gives you a lot of design flexibility. So you can realize your circuits in various ways and you can play around a lot in terms of your circuit. So these are already quite good advantages. And then the material that is used for this circuit is, as it is a circuit, you will need a substrate and you will need a metallization on top of it. The substrate we use is silicon, and the metallization is a superconductor, which is aluminum. And both of these materials are very familiar in the CMOS technology. So you already have a lot of background in terms of fabrication. You're not reinventing the wheel here. So we can already use a lot of CMOS technology, and most of the clean room fabrication can already be is already well established. So that is another advantage. But then on the downside, since it's superconductor, you need cryogenic environment. So you need to place your chips in these dilution refrigerators, bring them down to millikelvin temperatures and operate there. And then you also need very good amount of magnetic shielding to avoid flux noise and dephasing of your qubits. So all these things, again, put a limitation on your scalability. And the next thing is, since you're using these distributed elements of capacitor and inductor, you have a lot of crosstalk because of unwanted parasitic capacitive coupling and inductive coupling. And then this also creates a lot of issue. And then thinking about scalability, I think this is an issue in most of the qubit modalities, where you have to think about frequency collisions. So you can have either multiple modes, or you can have different frequencies throughout your circuit that are either qubit frequencies or your coupler resonator frequencies, all of them which will show up, and then you have to do a lot of bandwidth management. So as to say. Nevertheless, this is something that most of us know, that Google has demonstrated this 53 qubit entanglement record. And since then, superconducting qubits have been gaining a lot of attraction. And there are lots of companies that are already investing apart from Google. You have QTech, you have IBM-Q, Rigetti, IQM, and all of them are now working towards realizing 1,000 qubit. which is really ambitious, but yeah, that is where the research is going. And in terms of academia as well, most people are thinking of working towards 100 qubit architecture. So that is another promising modality. Our next architecture is trapped ions, where you basically trap an ion in an RF Paul trap. It can be a calcium ion or a strontium ion. And then you have only one electron in the outermost shell, which can again be used as a spin qubit with states 0 and 1, or you can use the hyperfine energy levels as well. So here, since you're trapping it, it interacts very little with the environment and gives you a very high coherence time and gate fidelities. And alongside that, unlike a superconducting circuit, you do not need very high or let's say very advanced cryogenic systems. Simple 4K cryostat is enough. You do not need a dilution refrigerator. But then on the downside, you need very ultra high vacuums. So there are pros and cons for different technologies. I cannot go into details of each one of them, but one thing can be said for sure, that the qubit race has just begun and it's far from over. So even though we have head starts in different directions, we cannot make a conclusive statement as to which modality is the best one. And then with regards to superconducting qubits, I would like to go a little bit further and talk about certain challenges involved in the scalability. So most prominently, there are, let's say, 4 areas with regards to scalability issues. One is material science and fabrication. So as I said, the superconducting element is made of aluminum, but there are people exploring other materials that has better or let's say lower 2-level system losses and thus can give better coherence. So like niobium, tantalum, niobium titanium nitride and others. And then there is something called as flip chip technology, which is used mostly in MEMS sensors, but now also being talked about in superconducting circuits, where you can have 2 different chips stacked on top of each other. And there the interconnects are made again of superconducting material like indium. So this will give you an advantage where on the bottom chip, you will put all your qubits, and on the top chip, you will put all the readout elements. And this way you can shrink your chip design a lot. And then another challenge in the fabrication is using bigger wafers, because in CMOS technology, this is the advantage that they get, that they can fab a lot of chips on a single wafer. But since we are using superconducting elements, you need Josephson junctions for your qubits. And this involves the shadow evaporation technique. And this limits, or rather, let's say, the quality of your Josephson junction varies across the wafer. So the bigger the wafer, the more variation, and this decreases your reliability and yield. Apart from this, you have another challenges in electrical and electronics engineering with regards to control systems and automation, pulse engineering, trying to decrease the crosstalk and losses due to like decoherence due to measurement, circuit designs and frequency collisions and all that. The next challenge is in cryogenics and thermal engineering with regards to miniaturizing the whole system, because the dilution refrigerator is quite a big device and also limits your operation time, because it takes a lot of time to cool and warm up. Then there is issues with thermal isolation. You need a better bath, and vibration isolations that can also cause some dephasing. And then finally, with regards to error correction and gate designs. So in the interest of time, this is where I will stop, but then we can continue more discussions further. Thanks.
Yeah, thank you so much, Achintya. Yeah, you've just confused us more now, because now.
Yeah, I mean, this is the situation right now. I mean, and to be honest, it's not like we have a clear answer, but we do have progress in multiple directions. So sure. Yeah, the confusion is a good confusion, let's say.
I think so. Abdullah has brought up many important points in the chat, but I think we'll take them up later. One question, since we're at this point, to all the panelists, I'd like to ask is, in terms of costs itself, in terms of the commercial viability of all these qubit modalities, what are your bets? And this is open to all our panelists.
If I may begin, I would say that, well, it depends on what you want to do. If you're talking about having a quantum computer at your home, superconducting qubits is nowhere near, because one of the major research challenge that is happening in terms of fundamental physics is finding a room temperature superconductor. And I mean, that's a Nobel Prize level research. It's really challenging. That is what I mean. So as long as that is nowhere in sight, it's going to be really difficult to maintain a cryogenic environment. And then you have it only in such niche companies and research institutes. But then again, you have a lot of advantages in terms of scalability, and that is why you see superconducting qubits researched a lot. But most of the qubit architectures require cryogenic environment to decrease thermal noise and vacuum, especially for trapped ions, for example. So this kind of puts a cost bar to everything. And then there are materials. So you need exotic materials like tantalum, niobium, maybe in future if they prove to be advantageous. And this substrate, silicon, instead of silicon, people are thinking of sapphire. So that again increases your cost a little bit. And then all of this also puts a cost bar. But maybe photonic qubits might be more cost efficient. I don't know. But with regards to superconducting qubits, this would be my take.
Yeah, I think photonic qubits, the biggest advantage is the temperature doesn't need to be so low. I mean, there is a little part where the temperature needs to be low, which is the coupler for the atom that couples and entangles the photon. Around that little region in the chip, the temperature needs to be controlled, so the atom does not like flip to different phases. But otherwise, the whole system is it's at room temperature. So at that level, if that's the criteria, then yes, it's far more cost efficient. But right now the lab looks really clumsy and huge. So I can't even imagine it being like a small laptop. But if I compare it to a supercomputer versus a laptop, then I think there's a possibility to a photonic quantum computer being a laptop as well.
And Devika, with regards to, so basically for photonic computing, you need a lot of photonic elements, right? Like beam splitter and whatnot. That can be miniaturized quite easily, I understand.
Exactly. Yes, they can be.
And and you would also need some laser sources, but I think even that can be miniaturized quite easily.
Yes.
And are the laser sources quite expensive?
I don't think so.
No,
because there are lots of them in the lab. I'm not an experimentalist, so I don't know the cost really, but it's not something that is like a roadblock.
I see.
The laser element. The biggest thing is like the most clumsy thing are the optical fibers, because there are lots of long optical fibers for the photons. But again, I think all of those things are manageable. I mean, this is what my intuition says for the future, but I think,
I just want to add one more point. Since you bring up room temperature qubits, there are various other room temperature qubits that are cooled down using these ground state cooling approaches. So you can do Doppler cooling or sideband cooling for trapped ions or neutral atoms. But that again involves laser and a lot of, let's say control systems. You need feedback cooling or sideband cooling. So it's not so easy and involves a lot of electronics. There again, the cost might be a bit higher, but you can have other, apart from photonic qubits, you can have other qubits as well that can operate at room temperature. So although you decrease the cryogenic cost, there is some other cost involved.
Right.
Okay. Yeah, Rajiv, you wanted to say something?
Yeah, so this, I think it's maybe a nice moment. If I could just share my screen for 1 second, I think let me give me I'm not able to yet, but I just wanted to say this has been really interesting, a nice perspective from Devika and Achintya. And so maybe to kind of zoom out a little bit, I don't think I can still share my screen. I need a permission. But to kind of give a zoom out a picture of the different modalities that there are, I just wanted to throw a slide up there just listing a few. And I think it's kind of a really exciting time. It's also nice to hear, you'll hear typically researchers in the field that are on the grounds will know all the problems that exist about their qubits. So it might seem funny for people working on photonics to talk about the problems in photonics, and the people working on superconducting qubits to talk about their problems there. But I think all different modalities have their advantages and disadvantages. And so I just wanted to list like the different potential options that people are working on, and say that, you know, the one that's going to win out, I think it's very unclear at this moment. It could be, you know, one of these. It could maybe be a combination of these. Eventually, it could maybe even be one that doesn't exist. And so, yeah, definitely to know more information. Well, the best way to know more information is to ask Devika and Achintya. But if they happen to not be around, there is a nice YouTube video that I thought was pretty interesting and like pretty overviewy. And also, I'll just put it in the chat. In the registration, Priya I'd given a link to kind of a primer on the different qubits. And I think that's a nice one too. But yeah, and as you can see, not only, you know, are there, you know, these things have different names, and Devika and Achintya talked about the differences, but you can also see in this picture, like, they're very different on the right, the way the labs look and the way the qubits are handled and stuff. So it's an exciting time, but nothing too insightful. Just kind of wanted to zoom out a little bit and talk about how there's like a lot going on, and it's an exciting time.
Yeah, thank you. That was actually super helpful, like a brief summary. Also, a very interesting point that you brought up is it could also be a combination of these modalities that we're probably going to end up with. And I can see that in terms of if you need networks joining quantum computers, I assume those networks are going to be photonic, but not sure. I haven't done my reading up on that. But yeah, please go ahead, Kishor. You've been raising your hand for a while.
Thanks for that. Yeah. So basically, you know, like, I mean, I think partially, I mean, I wanted to ask about, you know, this hybrid setup, and I think partially I was I got the answer, but let's say if Achintya could, you know, like expand on that. And there is another question that I have, you know, like, so what do people think about, you know, related to this Majorana qubit? So like, I mean, like, what is the current consensus? I mean, I saw some video in the past and like, no, okay, maybe one paper also, but like nothing published and like no data. So I mean, I would like to ask, you know, I mean, what's there at the moment? Like, what do experimentalists think? I mean,
again, not my area of expertise, but from whatever I know, it's highly ambitious in terms of finding these Majorana fermions. They are at states, as I see it, but yeah, no one has yet able to actually demonstrate it in practical application. So yeah, might be really tricky when it comes to this qubit race. Yeah, currently they don't have such a lead. And anyone researching in this domain, you know, knows the challenge and the ambition that they're holding on to. So yeah.
So like, do people believe that we saw that you know, that band gap, and you know, like, was the this Majorana fermion, like, was it really seen in the experiment? I mean,
in my understanding, I think no, Majorana fermions are not experimentally observed. The band gap comes from your solid state physics. So yes, but as I understand, like this for Majorana fermions, like you have these edge states, and to experimentally observe them, there are a lot of challenges. So it's not easy to experimentally observe them. Theoretically, you can predict them, but experimentally observing is a challenge. But again, not my area of expertise, so I cannot say more.
There was this Microsoft experiment, right? So I wanted to ask about that, right? There was some claim that they observed, and I mean, I am not following the, you know, like, I would say that, you know, like, yeah, at least you are an experimentalist. I'm like, you know, very far from this thing. So I wanted to understand, you know, like that, what do people think? Like, you know, I mean, are we going to have the qubit? You know, like, I mean, there was something like there was the paper, and then they say, okay, no, we haven't seen it. And then they say, okay, now we have seen it. So I mean, like, have we seen it? I mean, what is the current status?
To my knowledge, I think we haven't yet seen it. But again, I need to check if there is some new findings that I'm not aware of.
Okay. Yeah, maybe, I don't know if I can add a little bit of context to this for people who are not so familiar. I don't know, again, I haven't done experiments in like years, right? But just a little, like, I guess the news that I hear. So Majorana fermions are a type of qubit that people think exist and would like to engineer. They have the really advantageous capacity of being very, very noise resistant automatically. So the error correction overhead would, in theory, be very small if you can make Majorana fermion qubits. However, they're just very hard to make. And I think presumably not a single qubit has been demonstrated yet. There's also a little bit of drama around this field. As Kishor mentioned, like Microsoft are working on this. There were some papers that came out and then became retracted, and there are new papers that have come out now. And so that's why I think it is, at least for people that are not really, really into it, it's a bit hard to tell exactly what is happening. But as I think it's safe to say that we don't have, like they have, the claims were detecting certain signatures that show Majorana fermions, but I don't think anybody has like made a qubit or nobody has even claimed to make a qubit and hack the gate on it yet. So that's kind of the general perspective, but then yeah, people might have better insight or better details on this than I do. And there are some YouTube videos talking about the drama if you're interested as well, but that's a bit of a separate issue.
And just to add to what Rajiv said, yes, the advantage is that they are insulated, so to speak. So they have they're highly stable. They don't interact so much since they're at states. But on the downside, they also need cryogenic environment. So yeah.
Also, I don't mean to continue on this thread too much, but then you've been saying that they're isolated. So I assume then it's also hard to get them to interact, like to do gate operations on them. That's probably also
absolutely yes.
Okay.
That is why actually superconducting qubits they sit on a very nice sweet spot. They are not extremely isolated, but they are not extremely interacting and decohering too fast. There's 100 microseconds is quite a good sweet spot. And then you can play with these physical and logical qubits and do a lot of error correction and for scalability.
Okay, got it. So on that note of error correction and where we are and where we will get and how long it will take, maybe Kishor can share with us his perspectives on the work that he's been doing and what the outlook is like.
Yeah, so I think since I have only 5 minutes, yeah, like, so I have prepared like, like maybe 6-7 slides, something. I think I don't remember how many. And let's just, discuss a bit here. So yeah, I mean, there has been all these nice experiments. Actually, there is one more, like two from USTC. And yeah, but then do we really have demonstrated computational quantum advantage? That is the first question that you have to ask in the niche era before you can say whether we have, like useful quantum advantage. And the answer is not very clear, because last year there was a paper by, many people have tried to, simulate the experiment on their laptop and supercomputers and so on. And recently, there was a nice paper by many people, including Rohit Aranov and others, and Wazirani, and they found a polynomial time algorithm for noisy random circuit sampling. So, that's first thing. So let's say if somebody asks you, how do I trust that you have a quantum computer? So there are basically 3 approaches. You can just ask them to factor a large number. And under the assumption that factoring is hard, if they give you the correct answer, then, you will agree that, yeah, you have quantum computer. But this cannot be implemented in near term. So the feasibility is far term. Verifiability is easy because you can multiply number and check. And nobody can spoof it. So spoofability is hard. So this we cannot do. So in the near term, so this is gone. The other approach is, like the sampling task. This is what, like all these other experiments were. But then for this one, you need to verify if the output was correct. And for that, you need to do classical simulation. So you cannot really scale it. That's very hard. And then we do not have any complexity theoretic backing, which says that, like these experiments in the presence of a noise are hard to simulate, spoof. classically. So basically, this is also out, I would say, mostly for the near term. And then we have the other approach, interactive proofs. So in the interactive proof, basically in the I mean, I can discuss later. Basically, you interact and you try to make sure that if the other person really has a quantum computer or not, and interaction is very powerful. It's easy to verify, and the soundness is really, like, I mean, it's difficult to spoof, but the resource requirement is like at the moment the best, like 1,000 qubits and 10 to the power 4 depth, which is too much. So can one really make it current term? That's the challenge we have. So even before we go for the designing this algorithm and this and that, do we have the analog of Bell inequality violation in the computational setup? Bell inequality violation basically very much gives you clear separation between classical and quantum. On that, so, but that works for communication setup. For computation, we do not have a clear separation of them. So first you show useless, separation, and then you can show useful separation. So that's like, I would say the very first question that we are having at the moment. Yeah, like, forget about industrial scale useful or academically useful experiment. First, even analog of Bell experiment in the computation setup is very much lacking. Then the next question comes about practical quantum advantage, and there are many candidates, and many people know about VQE and all, and there are many different applications and many algorithms have been written and so on. Like, no need to go in detail. But then there are many challenges also. Like I have only mentioned a few different challenges, but then there are challenges related to trainability, the kind of landscape that we have, critical points, and so on. So these challenges needs to be taken care of. And then if you look at the recent quantum error correction experiment by Google, I mean, there they mentioned that in their Sycamore processors, the errors are typically between 1 in 10,000 to 1 in 100. On the other hand, to develop, in the quantum circuits that can solve industrially relevant problem, you need error rates in the range of 1 in 10 to the power 9 to 1 in 10 to the power 6. And how you can do that? You need error correction, because error mitigation will not help you reach there. So for that, basically, error correction is very much important. And to build good quantum error correction, there are many components that are required, but you also need to develop something called, like good decoders. So we need people from classical side to build it. And obviously, I don't have a lot of time, so I will just end with this small advertisement that, so if you are interested in know more about quantum error correction and all, I have been, involved in some tutorials where you can, learn about that. And the final tutorial will be on 25th of April, where I will discuss, this final thing. So basically, there is a lot of interesting thing going on. And even if you are interested from, let's say, not really, I would say, experiment point of view, but even from the physics point of view, or let's say maths point of view, quantum error correction is quite exciting topic. So yeah, that's it.
Thank you so much, Kishor. I think many questions in my head, but Rajiv, you can go first.
No, thank you. I appreciate that. Yeah, it was also a question to ask Kishor, like what are some, what do you think, and this is a subjective question, I suppose, what do you think are some interesting NISQ algorithms for you that you think will be implementable, either not necessarily for sure be useful, but promising, either currently or in the next few years before we get to the error correction?
Yeah, so that's a difficult question, but I think, maybe some analog quantum simulation algorithm, I would say. And some, so I mean, what is a NISQ? I mean, one can talk in the circuit model, or one can talk, not, someone need not talk in the circuit model. When we say NISQ, it's about noisy and the number of qubits or whatever, the device is not very large. So, I mean, circuits basically, like circuits are basically luxury of computer scientists. But on the other hand, what we have are Hamiltonians, and maybe if we can, take the Hamiltonians and engineer the pulse sequence and all in such a manner that cater to the, device topology, we can solve some problem. This is a very, very, very difficult problem because first, you have to even that will be useful, like what I'm saying, before doing anything useful, that will change the game, the moment you have that. But before that, even something useless, like Google's experiment. I'm not saying useless, useless as such, but industrially useless. Can you break so basically, when we talk about this kind of separation in the language of complexity theory, it means, basically breaking the extended church during thesis, that not all computers are same. So extended church theory says that, the classical computer, quantum computer, or, or whatever, the ABAC, the small, whatever different computers are, my laptop or a supercomputer, they are all same. It's just polynomial overhead, when you go from one to another. But then, quantum computer scientists don't believe. We have this BQPD. So how can you, experimentally, justify that? So to experimentally justify that, you need to build a device which can solve a problem which is provably classically hard, but quantumly you have implemented it and solve it, and that need not be useful. So yeah, I would say that definitely that will be first step, and the second step would be understanding the physics well, and also approaching it from the computer science angle, because it's a question about, I think it's a very multidisciplinary question, right? And also we need, experimentalists a lot, because let's think about, there are many large, so there are certain gates. Let's say if you can apply multi-control, multi-target gates, then your circuit depth can be reduced a lot. And for example, in the Rydberg setup, you can implement those kind of gates. So the question is about, always coming up with designing Hamiltonians, have you found our, I would say, nice setup where even though we call constant or polynomial overhead, these overheads are very important when you are qubit wise very poor. And we are poor at the moment qubit wise. So I think it will be very important in the near term to use whatever we have. And so I don't know, it's a very difficult question, Rajiv. Which question? Which question you can submit? It's $1 million question. I don't know.
I guess, maybe to make it a bit more specific, then it's what are you working on, or do you find interesting? I guess.
Okay. So I'm thinking, we will have to do some error correction and something, so somewhere in between, we will start making strides, when partial error correction and mitigation. So people have been looking at error mitigation and there is error correction, but one has to, connect the dot and basically some of the part you have, so let's say we know that for certain setups, you have biased noise. You do not have, a particular of noise that active. You have another kind of noise model. And then you could do something called approximate quantum error correction. So you could do approximate quantum error correction, and together with, when the errors has been reduced to a large extent, you can take help of error mitigation to, reduce the effect of noise, whatever is remaining there. So I think error correction and error mitigation, when they will operate in conjunction, so it's many things coming together, like the topology, Hamiltonian pulse sequence, whatever, design in a nice manner, choice of right problem, the gates that you are implementing. I mean, effectively, like when there should be the native gates, and then yeah, like some error correction, some error mitigation, and
Well,
some more imagination. Yeah. Sorry. Yeah.
can I ask a question?
Please go ahead. Yeah.
I want to ask the question to Kishore. Can you describe why the need for error mitigation when we have correction? Is it does it have less overhead? Is that the reason? Because
Yeah.
IBM has now announced that it's not doing active error correction. It's only going to do error mitigation.
Okay.
Do they have anything to back it up?
So yeah, I mean, so these are, I would say, like very personal view, like different researchers can have different view. So the way I see error correction and error mitigation, I mean, I haven't seen a proper research paper, I mean, these are my thoughts, like basically. So error mitigation, I mean, okay, or maybe other people are also thinking, but I haven't read it anywhere. Like, I'm just putting my perspective. So error mitigation, the way I think of it, I mean, and many other people also think of it, is as you are basically, it's like you are using redundancy, but the redundancy is in time, like you are taking multiple samples. Your circuit depth is same, but you are taking multiple samples. So that will cost you more time. And then by taking multiple samples, you are able to infer noiseless expectation value from noisy expectation values. That's how I can think of error mitigation. So there is redundancy involved, but in time. Now you have in quantum error correction, you have redundancy involved in space. So basically you have more qubits. So there you do not take multiple samples, but you have more qubits. Now the question is that should we just include redundancy in space, or should we include redundancy in time? Maybe, when we are resource wise not very good, maybe some redundancy in space, some redundancy in time, and the right kind of balance trade-off should be, maintained so that you can do something non-trivial. So that's how I would think. I haven't formalized this, but I would like to, work and maybe come up with one protocol where there is some, I don't know, I can take 513 code and some error mitigation and come up with, an approach. Like it can be a good research problem also if somebody is interested, that come up with a scheme which is partially error mitigated, partially, error corrected. And so it's like kind of an intermediate thing. I mean, that one has to come up with. And that will be like very nice a thread which, takes you from mitigation to correction. But yeah, I don't know.
And maybe if I can add just a comment on that. So yeah, I think to that point of space versus time. So I mean, as many of you know much better than I do, in the quantum error correction, in addition to requiring more qubits, you need to perform like magic state distillation to make your T state. So there is also a little bit of those overheads in terms of time as well. But of course, if you can do all that, you can get very, very good computations with very low errors. Error mitigation, there are typically not so many of these like hidden like other overheads. So you kind of just, as Kishore mentioned, you run the circuit a bunch of times. You don't need to add more qubits, and then you take your results. However, there's a ceiling to which you can correct errors in this error mitigation, right? So I think another, it's like as Kishore mentioned, to create this thread, we can do error mitigation now. And so if you can find some NISQ algorithm that is useful and that requires just like you need to get good enough in the error, then maybe error mitigation can help you solve that problem. But I don't think it's it's not a long-term solution, and so yeah, you would need eventually this thread. But maybe that's why error mitigation is something that's interesting in the short to medium term. And then I really like this idea that Kishore brought up, which is really cool, to make this thread. So, and which I just heard about today. So
yeah, so I just wonder why. I mean, I've seen a lot of people that are using IBM devices do a certain algorithm or talk about a certain application and then say we applied error mitigation and it got a bit better. But, and I assume we're not able to do that with error correction now because of the resource constraint. Is that why nobody has worked on both together? Or?
Yeah, so error correction, like you need some non-triviality experiment from the experimental side to just even cross the break-even point. Like, I mean, so the break-even point is basically, you know, like you have a bunch of qubits and taken together, let's say, you develop a logical qubit. And the lifetime of a logical qubit should be at least better than, you know, like the best qubit that you have. If not, you will just use the best qubit. So the point where this, you know, like, like this power shift happens, that's called the, you know, the break-even point. So achieving break-even point, it's a non-trivial task. And so on the other hand, you can take samples, you know, like, I mean, and we have all the time in the world at the moment. Our NISQ algorithms are, I mean, our devices are not that good, but, you know, like we keep on running 2-qubit circuits, you know, like, and 5-qubit circuit, and see, I mean, that will not give us anything useful, but at least you can play with error mitigation. But even playing with the notion of error correction, that will require experimental non-triviality. But let's imagine, you know, like fast forward, we are in like in 2028 or something, where we have, you know, like concatenation up to layer 2. So we know that, or like you concatenate your code and you go from, you know, like P to P square to PQ, like where P is, you know, like error probability. So you keep on decreasing by concatenating your code. Now, we know that, you know, like in error mitigation, when you have a large amount of noise, then you need to take, in certain cases, exponentially many samples. But then error correction helps you decrease the error exponentially. So then the question is, and does not require, and the resource requirement is only polylog. So then the question is, let's say we have managed to, you know, like concatenate up to level 2 or level 3. And then we also, you know, like we can do some mitigation by taking more samples, then that will be able to, I think one can even numerically at least forget experiment. I think one project could be that some guy, you know, like numerically just tries to explore it and see how does this thing, you know, like explore. And then some theorems and whatever could be proved. And when the devices are mature, then, you know, like one can experimentally also see this. Yeah.
Very interesting perspective. Unfortunately, we're running behind. So, and all of this, I guess, is important, or a lot of us in this particular discussion, even those who are attending, are interested in this area of error correction and when and what, because of the applications that quantum computing promises. So I'd like Rajiv to maybe take us through what it looks like in terms of applications and, more importantly, funding and investments that quantum computing companies are getting today. How that's happening. And
thank you. Yeah, so I think maybe what I'll permit myself to do is be like a bit of a bridge between us talking about the technical issues and talking about the funding. To be very honest, Anuj, who's going to be speaking after me, will know a lot more detail. So maybe I can just be the bridge, and then he can take it from there. Because I've done a little bit of work on the hardware side in my PhD days. And then a little correction, I wasn't the head of R&D at Goldman. I was just a mere scientist there. But in my time there, I've worked a little bit on algorithms. So maybe to start on that bridge, kind of take a step back and look a little bit at, I have like 3 slides. So what do people that do quantum computing research, what do they do as a whole, right? And there's kind of, all of us are just trying to do one of 2 things. We're either trying to build more powerful quantum computers, or we're trying to figure out how to use these quantum computers. And these 2 aspects are not mutually like exclusive, right? But that's basically what we're trying to do, one of these 2 things. And then we don't sit and tackle like this big problem. We tackle kind of subfields of this problem. And these subfields, I've just listed a few of them here, and they kind of lie typically somewhere in this spectrum, right? So we've talked about quantum hardware, quantum error correction, quantum algorithms a little bit as well. Kishor has mentioned those, but the focus today is on quantum hardware. And as you can see, I've put it, kind of mostly to the left. I mean, people that work on building physically these computers, they think mostly about on a day-to-day basis how to make these quantum computers, like how to add more qubits, how to reduce the noise, and how to make the gates faster, right? And a small but important part is also this right-hand side of trying to understand how to make the quantum computers more useful. So we've kind of taken this big picture and zoomed into hardware. And so yeah, I can talk a little bit about funding. And given I think I have a little bit of knowledge, but and Priya, you can do as you feel. Maybe my suggestions I can talk a little bit, and then Anuj can even go right after. I don't know if there is useful to pause for questions in between, but I will leave that to you because my thing is like very hand wavy in general. So I wanted to just flash up this slide. These are some numbers. I think looking for how much money is invested in quantum computing hardware is a bit of it's a little bit unclear because you can have funding from different sources. Not all of the funding is public, right? Especially things like companies funding their own work. They may not tell you how much money they're investing. This slide, by the way, just a legal note. I don't know why it says confidential and proprietary at the bottom because I literally got this off their website. So, but it's quite nice actually. And you can see that most of this is for quantum efforts total. So it's not, specific quantum computing hardware, but it gives a good order of magnitude estimate, right? So this is 4,000 crore rupees, this big 24, or no, sorry, not 4,000 crore rupees, it's more than that. But what I wanted to say is that, yeah, so it's $24 billion. And this is basically just like government funding, mostly that's on this slide, maybe with a little bit of startup funding. So, okay, what does that mean in terms of funding for hardware? I would say it gives a good upper bound, right? So if you have roughly this much invested in all of quantum, excluding what the companies maybe are investing, you're not going to get, the amount invested in hardware is a subset. So we're definitely not investing like 250 billion in quantum hardware, and we're probably investing more than 2 billion in quantum hardware worldwide. So it's somewhere, this gives you an order of magnitude scale. Maybe to be a bit more specific about companies, so as Devika mentioned early on, I will talk a little bit about PsiQuantum. They are the startup company working on photonics. They are, I believe, the quantum computing hardware company to have raised the most money, which is roughly $500 million, so 500 million. And that is roughly 4,000 crore rupees, so to change that into rupees. It's not unreasonable to think that companies like Google, Microsoft, and the other big companies are also investing roughly that amount of money in their hardware. So yeah, so to give you, that's to hopefully give you a bit of a scale. And maybe the last thing I'll say is to relativize the scale of investing of quantum computing versus, or quantum technologies versus, a much bigger technology we have today, which is AI. So here are some numbers. They're not super accurate, right? These are estimates. And these are the relative market values of the industry. So market value, kind of like a very hand-wavy way to think about it, is not how much money has been invested, but if you were to buy it, how much you should buy it such that you can eventually make a profit from it. So in 2028, the quantum computing market is valued to be $4 billion US. And just to put some other numbers today, or I guess last year, the GPU and AI markets were valued to be 40 billion and $100 billion. So 3 lakh crore rupees and 8 lakh crore rupees. So that's to say, the takeaway from this is that 5 years from now, the whole quantum computing market will be worth 1/10 of what the AI market, 1/10 or 1/20th of what the AI market is worth today. So that's a nice relative scale. It's still a lot, right? Something that's worth 1/20th of what the whole AI market is worth today is a lot of money, but it's to kind of show a little bit the nascency of quantum computing. So that's like my kind of hand-wavy slides on the funding. Hopefully it gives you a sense of the type of money involved. And yeah, we can either take a discussion now, or I'm also, if Anuj wants to, if you think Anuj should go straight away, that's fine by me too. I think that's what I got.
Yeah, sure. But mainly this is anything but hand wavy. I don't think any of us had this sort of clarity with regards to the numbers, and you made it super nice by doing the USD and Indian rupees. So thank you so much for that. If the panelists, oh yeah, Achintya.
Yeah, so Rajiv, very nice and very crisp, presentation. Just a question. So these investment which you show, is it specifically for quantum computers, or does it also include the, peripheral technology? Because when you are realizing a quantum computer, well, most of the funding has gone into, researching the materials and the realization of the chips. But then you also need research in cryogenics, which is not quantum computing, but an assisted technology, ultra high vacuums, lasers, for example. I don't know, a lot of research or let's say funding goes into clean room fabrication. India currently also has a lot of clean rooms that are developing, but then they are, let's say, grade 100 clean rooms, not those class 100, not class 1. So, a lot of money is distributed in these peripheral elements. So when you pose these numbers, what were they for? The actual qubits or qubit research, or peripheral included?
Yeah, you're gonna expose my ignorance now by asking this question, but it is a great question. So yes, the short answer is I don't know, but I would say to elaborate maybe a little bit.
I'll add to that. So it is complete. Please. All the quantum technologies. These numbers which are there and which are published on yearly basis, whether it is Eureka or some other source, that is actually covering the complete all the verticals of quantum technology, whether it is quantum communication, cryptography, sensing, materials, everything.
But it's not, I would argue so. So for example, in this slide on the bottom left, you see that it's the US National Quantum Initiative is 1.2 billion. So this is in the form of grants. So presumably if, for example, building a clean room, you can use that for many, many things, not just quantum computing. Yes. And I suppose my guess would be that, the money used to build a clean room may not come from a grant specific to quantum computing. On the other hand, something like
that's true.
Building microwave controllers for quantum computers, maybe some of it might come. And then, of course, if you're building a quantum computer, if you're saying I want qubits, then if you're like a national lab, most probably that money is coming from.
That's actually true. There's a lot of overlap with other classical technologies like CMOS technology, for example, and then the MEMS sensors, especially a lot of overlap with MEMS sensors, and various other quantum technologies like even Anuj was mentioning quantum sensing and quantum communication. So yeah, it's a collaborative effort, and it's good to know the numbers. In my personal opinion, it's still not enough money spent compared to, the CMOS technology or AI or other fundings. But yeah, it's a good start in the right direction. Yes.
Yeah, it'll cost a lot of money to build a quantum computer. I agree.
I think Anuj can also tell us a little more about how much of this money is actually being used where. I recently heard, and I might be completely wrong, but I'm just going to put this out there, that so the Indian fund, which was the National Quantum Mission here, which was 8,000 crore, has now been reduced to 6.5 thousand crore. So this is just something I picked up somewhere. Might be completely wrong, but so, and I think that a lot of people are saying that they're not receiving the money. So also in the context of India and the communication conclave that happened, if you can tell us more about these points that Rajiv brought up.
Yeah, so I'll give a little bit background. So first of all, whenever we talk about any of the quantum mission for any country, there is a strategy, and strategy has 4 components. So one of the component being the mission itself. So for the mission itself, it is like the National Mission for Quantum Technology and Application, which we know was approved $1 billion or 8,000 crores, like in the budget of 2020. And then coming to the vision part of it. So vision is second component. So vision is what need to be understood, and considering this particular vision, all the quantum ecosystem, whether they are from the quantum computing, from quantum sensing, from quantum communication, or quantum materials, all are actually considering and they are working in tandem with this particular vision, which is around the like the development of technologies and standards. And whenever like the focus is when I talk about the technologies, the main focus is there on the telecommunication technologies and standards. And there is a lot of stress on the standards. The reason for that has been like if I talk about like comparing it to some other standards which were actually there in the telecom sector, the 3G, 4G, and even the 5G, like it was considered that India was actually lagging behind. The thing is like India never attempted to explore in those particular standards, but lately we saw that there were certain developments. India came up with its own 3G and 5G infrastructure, and like recently there was a launch of even the 6G standardization where India will be leading. And the thing is that the organization, the enterprises which are there, okay, like if I talk about in context like Reliance or Bharti Airtel, these organizations, if these standards doesn't exist in India, they will definitely look for something which is actually outside, okay. And that is the main focus of actually this particular mission, that the standard should be focused and India should be leading in standardization. And that's why there was a recent paper, a test guide, I would say, which was launched by TEC jointly with DOT for the QKD and for the quantum safe and cryptography. Okay, and this is one of them, and there will be another series, some other test guides or standards will be also coming up. Then coming to the part of the what is the goal, ultimate goal, what India wants to achieve. So in terms of the timelines, if I talk about, India is not targeting aggressively to reach like 1,000 qubit or 1 billion qubit. India is targeting for an indigenous like a quantum computer, which like if you ask me about the sort of actually technologies, it could be a superconducting, it could be a photonic quantum computer, but India is only targeting for a 50 qubit quantum computer by the year 2026-27, and that is where will be the like it is considered to be a inflection point where there is a projection like from starting onwards from the 2026 onward, this quantum technologies will be and quantum computing altogether, they would be contributing approximately 2.5 billion to 5.8 billion to the economy, and then it's scaling up to you won't believe it, but even I actually, when I saw those figures, it is one of the NESCOM report I came across. They are claiming that till the end of like 2030, it can actually reach up to 280 billion. All I'm talking about in totality, all the quantum technologies will be adding that much to the Indian economy itself. So you can consider the sort of actually attention and focus which is there from the Indian government, and it is quite right. I think what coming to the point of Priya, that there was, though this was actually declared in year of 2020, but due to this particular COVID scenario, nothing or considerable, I would say, not, I'm not saying that there's nothing happened, but nothing considerable happened which was actually available for access to the in public with regards to this particular mission. And that's why now aggressively this particular mission is being rolled out. And so far, the discussion which I have heard and this like all the announcements which are there from Department of Technology or DST, because this particular project runs under DST, there is no change in actually this particular budget of 8,000 crore, that is 1 billion. It is still maintained. Yes, funding is one thing which is now being aggressively being taken up, and the same point was raised during this particular communication conclave which happened Delhi during like 27th and 28th of March. Same thing. The main focus was that not only the government organizations which are there, the research organization, the academia, and the defense, ISRO, DRDO, and some only contributes to this particular quantum mission, but also some private players. And India would be actually relying, I think, just to name few of them, like QNU Labs is one of the prominent one, which is there. Q Labs is there, and apart from that, this particular, there was a remarkable work which has been done by the Raman Research Institute, And like you might have actually heard also that a few days after this particular quantum conclave, there was a like announcement which was also done by the Raban Research Institute that they achieved a sort of a quantum safe communication from like a static source to a mobile recipient. And this was actually a news of 1st of April. I know it is not to us, not meant for fooling, but it is a real thing. And that is a very great achievement because until now, there was all attempt was to do a point-to-point actually quantum safe communication. And there was another thing which was actually also declared, you might have actually came across that there is a gravitational wave center which is actually coming up with in Maharashtra. And the investment for that is also of the range of 2,600 crores. And this is sort of a LEGO, like, which is sort of, I would say, same sort of setup which is actually there in US. If I'm not wrong, it is in Louisiana and in Washington, DC. So this is the third one. Okay, it is a laser interferometer gravitational wave observatory. Okay, that is actually coming up in Maharashtra. So there are a lot of actually things which actually got delayed due to this particular, I would say, COVID thing, but now they are slowly and gradually actually gearing up. And it was really exciting to understand that though we talk about a lot of actually research and those things, but there are on the basis of there are certain specializations also some of the research institutes which are actually carrying out. So there is when we talk about the cryogenic control, so IIT Delhi is actually leading in that. So in quantum materials, it is there are certain actually duplication of work is also going on, but there are certain specialization I'm talking about where the focus is there. So IIT Bombay is actually working on the quantum materials. Quantum sensor is something which is actually there for the ISR Pune. IIT Madras, as I actually mentioned earlier also, and there are certain startups associated with that. Quantum photonics and quantum devices is one thing which is ISC Bangalore is working, and DRDO, ISRO, they work in tandem with all these actually research institutes, academics to their focus is actually, if I talk about specifically about the DRDO, so they are actually working on the quantum seismic imaging. They are talking working on the quantum radars, okay, which will if quantum radars are actually we start using them, then stealth technology, which is actually the your F-22 Raptor will be obsolete technology. Okay, so you can understand the capability of quantum radars. And like even the DOT, the 6G project which is there of the DOT, that will be completely relying on this particular quantum technologies. To be specific, QKD and quantum random number generations, those two actually solutions are something which India is like the DOT is focusing a lot, and the CDOT, the Center of Development of Telematics, that has been actually declared as a one of the center organization which will be leading all this particular communication technologies, and they already have their own QKD setup, and most QKD and as well as the post quantum cryptography PQC solutions. And there are something else also, like even like the Raman Research Institute, they have started working with Indian Navy for the secure setup. So most of this is actually, like if I talk about, if you ask me, the 92% of the projects which are running in India, they are under this particular umbrella of all the research institutes and like defense area only. Only hardly like 8% of that actually is contributed by the private sector. But slowly and gradually, the projection which was actually given and declared that what DOT actually considered that by the year 2028 there will be 44 billion investment which will be going into the quantum technologies, and within that on a yearly basis approximately 2 billion investment will be directly going into the quantum technology startup itself. The main focus, if you ask me, the reason why there is no thrust being visible on quantum computing and more focuses on quantum communication. The obvious reason is that ultimately the focus is actually to first of all secure the communication. because this is not something which India is actually targeting for the general purpose. And there is a precursor mission also which need to be actually understood, which was the National Supercomputing Mission of the year 2015, which will be also one of giving the one of the directive to the national quantum computing mission for the National Mission for Quantum Computing. All the projects which are actually running in that national supercomputing mission, they would be also it will be this all quantum computing developments will be contributing to that supercomputing mission as well. Okay, so they will be running it beside, and CDAC is actually leading that particular initiative. So, and just a last thing, which I just want to point out, I think many of you might have actually came across also this particular part also, that in this 2023, the General Conference of United Nations and both UNESCO, they are actually targeting to declare the year 2025 as the International Year of Quantum Science and Technology. And India is quite actually ambitious about the same, and they are actually thinking that by that time, at least in terms of actually technologies, India is actually declared as one of the leader of quantum technologies. So I think that's all from my side.
That is quite encouraging for any of us sitting here in India who want to pursue quantum technology, be it communications or computing or even sensing. There is a lot going on in research institutes, in academia, as well as in industry. But as a group that is sitting in different parts of the world, we're literally all sitting somewhere else. It's Anuj and I are here in India. A question I had was, so Anuj started off with the context of the conclave, the communication conclave that happened, and then the telecommunications ministry announced that they have the first operational QKD link. And I'm not sure what the state of the art in Singapore is, but I think AWS collaborated recently with CQT, I think, in Singapore, and they had a 3-kilometer QKD link that they realized. But then back in 2017 itself, if I'm not wrong, China already had a 2,000 plus 2,600 terrestrial and satellite communication link. So just in terms of the discrepancy around the world, and as researchers in the field, what does it look like to all of you, and just why do you think such a great discrepancy exists, and what can we do about it? How does it affect you primarily?
So, do you mean, by the way, are you specific to QKD or general?
I mean, that's just an example. I do think that other countries are leading in, but there is still a discrepancy, is what I assume and what I'm able to see. Correct me if I'm wrong, but yeah, just all of your perspectives on that.
Maybe I can speak a bit about Singapore side. Like, I mean, I'm not the right person to talk, I would say, but I can give some perspective, based on, so I worked at security back in the past, and then now I'm at A-Star. And so here, basically, there are 3 different nodes. So one is National Quantum Computing Hub. So earlier we had security, and, at security, there were, researchers who are from all over the world. So for example, my supervisors, they were from NQE and Oxford, like 2 of them. So it was like a center from people all over the world over there. But then recently, government, put more money, and now there is a parent organization called National Quantum Computing Hub. Under that, security, A-Star, and many of them are there. So that will look at quantum computing. Then there is a National Quantum Safe Network, which is interested in, building the communication link and all. So Singapore is very small, right? It's like 28 kilometer length and 30 kilometer, maybe like 700. It's like the size is half of Delhi. So, I mean, basically, the requirements are not very high in terms of, so even 3 kilometer is a big distance, I would say, So I mean, in terms of communication, I would say there has been some really good researchers here at CQT, and they have been like, leading, I would say, like, I mean, many of you know, like, there's no need to name them, but they're the many of them, like, world leading researchers they are here. On the computing side, I think there were not many researchers. Like, there are researchers, but I think not much work has been done on the computing side. And but yeah, like now also, like, I would say in the computing side, hardware wise, there are not really, like quantum computers, which are, I don't know, like, I mean, now there are plans to purchase quantum computers and all, maybe, I think, I don't know, from different vendors. At the moment, people are mostly using cloud computers. I mean, like, there are some groups which are working on superconducting qubits and all, but yeah, like 10 qubits or something. I think one of the groups has 10 qubit. There are ion traps people also. Yeah, there is a big effort on photonics going on. But I would say, like, compared to US or China, I would say, like, Singapore is nowhere when it comes to computing. At the side of sensors, I think there is some good progress going on. So I would say in terms of, so Singapore was one of the first places where, like a dedicated center for quantum came, like, the Center for Quantum Technology, like in 2007. At that time, there was not many quantum centers around the world. They were like first IQC, then CQT, and then were like in US, and then many centers started coming. So, but yeah, I think, and there is also, I believe, some funding issue probably. I mean, a country like China maybe can fund, like 10 billion and can really, like start soon and like, I mean, start late, but, like reach there wherever they want to reach faster. But I think after this National Quantum Computing Hub, there's some really good effort, like many people trying to, so let's see like what happens. So yeah.
Yeah, okay.
That's my
Singapore.
but like, but all this, like, keep in mind that it might be very biased. Like, I'm not an expert, and I'm also not a representative of from the experimental side what's going on. It's all just what I hear in the corridors and from my colleagues, and like based on that, yeah.
Which is sort of reflective of what is going on in general. So, yeah. Yeah. I think I saw Rajiv's hand up and.
I can talk a little bit about just on the Swiss side. I'm not currently in Switzerland, but I will be next month, and that's where I live. Yeah, I think Switzerland also has a bunch of quantum initiatives there in terms of like quantum computing and sensing. And I think the biggest one is also QKD. They're setting up, actually, a Swiss company is setting up QKD links in South Korea commercially between government buildings in South Korea. There's a lot of effort going on. But I wanted to, and I see like, get more into this idea, and this is maybe a personal point of view, of this like inflection point that Anuj had mentioned. So, I think I don't know, very naively, I'd say the main reason India is a little bit behind countries like US and China, and maybe even Switzerland and Singapore, is the funding, right? If you just, because India has a ton of very smart, hardworking people, right? Genuine people. So you throw money at it, those people, you can empower them to do well. But I don't think it's so far behind that it's like lost. We already have a pretty good infrastructure to kick things off. So I think what I'm really interested to see is kind of like, sure, in this race where things are moving a bit slowly, India may be a little bit behind from my personal point of view, but there's no reason at any point, not just India, but any country could, make some really big strides once they reach, a certain level, which it seems like India might reach very soon. So I just kind of, I would just maybe argue that the progression is not necessarily like linear, and I don't think India is so far behind that it has to like, it has to worry about that. But I think as long as they continue to like focus and improve and increase the quantum efforts, yeah. But that's just a kind of a point of view. But there are lots of other hands up, so I'll let them take over.
Yeah, Achintya.
Yeah, thanks. So I want to like zoom out a little bit and talk about the bird's eye view picture over here. Again, building upon what Rajiv already mentioned. So first thing, again, lots of biased opinions here and debatable. But first thing I would like to say that we also need to encourage a lot of research in quantum sensing. Speaking of quantum technology on a whole, again, for multiple reasons. Firstly, being that quantum sensor has a promise or potential of being realized sooner than quantum computers. So, I mean, let's be realistic. You are not going to have a quantum computer in the next 10 years, something that is fully functioning. Everyone in the academia as well as industry are well aware of this, and it's I mean, what do you say? It's a known truth. So, but with regards to quantum sensors, you have this time that in the next 5 to 10 years you might have some good quantum sensors. There are already a lot of companies that are what do you say, that are selling commercial quantum sensors. There was some discussion in the chat regarding NV centers, so they are used for magnetometry, and magnetometry has in itself has a lot of applications, from material science investigation to, let's say, aerospace and various other fields, even in what do you say, geospatial imaging, and lots of others. So this is where India can actually benefit. Again, the cost is smaller than that required for quantum computing. I'm sure there is research going on, but maybe not to the scale that is expected. I don't know. Another advantage that you get from having research aside from quantum computing in sensing and communication is this cross collaboration. So there's a lot of overlap between each of these branches or let's say fields of quantum computing. So for example, talking of superconducting qubits, which is highly researched, you can use superconducting circuits or qubits for sensing application as well. So you can use it for, what do you say, commercial applications, like the ones I mentioned earlier, especially in terms of magnetometry, because a squid itself is a highly sensitive magnetometer. You can use it for defense applications. There are a lot of applications in defense with regards to quantum sensing with superconducting circuits as well. And then you can also use it for fundamental physics investigation. Like, for example, even my PhD is focused in testing the limits of quantum mechanics. You can use it for a lot of it for dark matter investigation. So these LIGO-based sensors, which Anuj was earlier talking about, these such detectors can be used for detecting dark matters, not specifically LIGO, but various such type of detectors. So you can have an array of superconducting qubits and then see some weak interaction with electromagnetic radiation, and then investigate into these weakly interacting massive particles, which is a candidate for dark matter. So you can do these kind of things. And then another advantage that you get is again, continuing this point of cross collaboration is research expertise. So let's say a group investigating in quantum sensing can contribute a lot to quantum computing and vice versa. So for example, we use a lot of expertise in Josephson junction coming from quantum computing group. And in future, I'm sure quantum computing would be needing a lot of expertise in vibration isolation, which comes from the sensing group, because we need vibration isolation a lot. And then magnetic shielding is again something that is common. So what do you say? It's like, what do you say? Typical financial investment, right? You diversify your portfolio and investigate your, you put eggs in different baskets, so to speak. So this is one big comment. And second is investing in peripheral technologies. So because when it comes to hardware, it's not just about algorithms and gates and qubits, but it's also about these peripheral technology of cryogenics and vacuum chambers and fabrication, clean room materials, and all these different things. So one big point that usually comes up when it comes to funding, especially in superconducting qubits, is cryogenics. So if you Google the word quantum computer, the first shiny golden chandelier looking image that pops up is a dilution refrigerator. And that thing, to my knowledge, costs somewhere around 500 million, €500,000 euros. Yeah, so that's extremely costly in itself. And then if we can have some startups that are in research, there are startups in Europe, I don't know if India has one, that are researching and miniaturizing this cryogenic system. That would be really great. And then again, cross collaboration between clean room technologies, vacuum technologies, because the more you have things in-house, the more you drive down the cost. And this is not just an initial cost, but then also maintenance and whatnot, because I mean, yeah, this is a really huge, what do you say, overhead when it comes to cost for quantum technologies in general. So we need to really focus towards the peripherals more than what we are doing right now. That's all.
Really nice point, actually. I've been making note. Yeah, Devika, you had your hand raised.
Yeah, I just want to add the only thing that I think everybody else missed out is that there's a social aspect to why India is lagging behind slightly, because we are not a startup nation. We usually like to play it safe. I mean, when you grow up in India, your parents tell you to either become a doctor or an engineer. This was like in the last generation. So you have a steady income, and the startup culture is just coming up in India. Now there are a lot of new startups, not just in quantum setup, but also in other like plant-based, and they're trying out new things. So I think with that aspect changing in India, it will catch up pretty quickly. Because like Achintya and Rajiv and everybody else added, we have the right amount of research and very smart people as well. And now that the government is putting in money in it, I think we will catch up. So I'm pretty optimistic about that.
Yes, that's actually a good point because now this what do you say, culture is being broken, that we have to play safe and people are actually taking risks, and it would be really nice because India is known for its low cost of labor, low cost of manufacturing, and that can be really utilized if one strategizes really well in that direction.
Right. Yeah, I agree.
Right. Yeah, I think we hadn't spoken about the social and socio-economic approach that India usually takes. But yeah, that's a very good point. Yeah, and I think Anuj, you've been waiting to say something.
Yeah, so I think there are a few points. So first to answer, I think Achintya and Devika, just to I don't know like how much you are connected to the startup ecosystem of India, but I just want to actually highlight like India is one of the second, I think, country where the startup culture and ecosystem is actually growing at a very fast pace, and it is actually contributing quite hugely, like a 1 or 2% of the GDP. If it is actually started contributing, then you can consider like what sort of actually scale it is actually coming up. So I think just stopping there on that particular part. So like in terms of actually quantum communication, when I actually mentioned, so quantum communication, it is not only the fiber optics where the CDOT and the IITs and ISRs are actually working, but there is a free space actually communication also, which has been focused, because that is also where China also invested like approximately 20 billion they have invested so far. Like in public, it is 17 billion, but in reality, it is more than 20 billion actually. And they're aggressively doing it. And that is actually consists of both the free space communication as well as the fiber optic, that are still network. So same thing India is also doing. So ISRO and DRDO, like around with the Raman Research Institute, as I mentioned, they have been actually working on the same. And there is a very interesting thing which actually was attempted by India, might have been done in other countries also. That there is an open hackathon of 2023 where like the Minister of Mr. Ashwini Vaishnav, you might have heard of him. So he actually declared there is a hackathon that if you can hack there is a link, a secure link between the Sanchar Bhavan, and that is based in Delhi, and the NIC Center, which is again also based in Delhi. So it is a QKD link. So like it is an open hackathon where hackers can actually hack, are allowed to hack. They have been like invited to hack that particular link. And there is a PQC setup also, and if they are able to hack, per hack they are awarding 10 lakhs. So it is open to everybody. Okay, so if you want to hack, and if you are a hacker, I think nature, then you are also open to do that, and per hack. So if even you can be you can, what you say, kaun banega crorepati, you can be crorepati in one day. If you attempt 10, and in all those 10 attempts you are actually able to hack that, then you can be a crorepati in a day. Okay, so that is like something which I want to actually highlight. And one of the last thing which I also want to highlight is there is an initiative from Department of Telecom that they are actually coming up with there's again something which has been initiated, that is actually a quantum alliance. Because what is actually happening, this quantum material sensing, computing, whatever vertical we talk about, there's a lot of duplication happening. So something, if it is happening in ISR Pune, it might be happening at IIT Kharagpur or Madras or somewhere else. And what is the progress? Then, and that is the issue with, that is one of the main issue with funding also. One of the main reason which DOT had actually also highlighted, because there is no such quantum alliance at India, like, at the government level, if I talk about. And that is the reason, like, it is very difficult to, because what is actually, for example, it is an initiative of the quantum communication if it has to be funded. But because there is a lot of duplication happening, like, for example, there's a iHub, QTF at ISR Pune, which is there. If they are working on something sensors, and at the same time, Kharagpur was also working, and at the same time, CDOT required some QKD sensors. Okay, they wanted it for their own appliances. They had to actually import it because they were not aware at what level, what is the status of that particular development, and they have to import it. And that is something, all these gaps have been identified. And like, I think might be in next upcoming year, you will see that there's a quantum alliance, which is in active in India. And that will be covering not only the government organization, but also the private players, the startup mainly. Okay, so that is something which need to be like, need to closely actually monitor. And funding should not be a challenge now onwards. The reason for that is like India is also understood because there is a lot of confidential data which even I cannot actually share, because I work with certain actually other organizations also. So, but the way, if I talk about specifically the Army is actually targeting not only the point-to-point or point-to mobile sort of actually QKD setup. They are actually targeting for the hub and spoke type of actually architecture. Okay, where like a multi-point actually communication, secure communication is actually possible. And this is something which will be also getting connected to, if I think most of you might be already aware, I was mentioning about the National Supercomputing Mission. So this will be actually somewhere connected to that particular supercomputing. There is a grid also. I don't know if you are aware that like all these, there are 27 sites which actually host a computing power of like approximately, it is in another next 2-3 years, we'll be reaching 64 petaflops. Computing power, and that is actually connected through a grid. Okay, and it is called the National Knowledge Network. Okay. And that is what like even this, all these quantum computing centers will also be connected to going forward. So this is something which need to closely actually monitor. There are a lot of developments, might not be, as I already mentioned, when 92% of the things are in government. So that means it is confidential. And that is the reason nobody was aware like what was actually happening. But there is a lot of things that actually happened, and quantum communication, you would see in next 2-3 years, India would be surpassing what efforts China has actually invested. I'm pretty much sure about that. The way India is actually taking up or aggressively taking up the quantum communication part.
Yeah, Achintya, yeah. Yeah, Achintya, you've got your hand raised.
Yeah, thanks. So just again, continuing what has been spoken up until now, especially by Anuj. So Anuj, at the start, you mentioned about the fact that India is kind of a fertile soil for startups. I agree with you on that. However, one needs to distinguish between software startups and hardware startups. And correct me if I'm wrong, but in my understanding, a lot of startups are software based and not hardware based. The challenges are quite understandable. Well, first thing, the initial cost for software startups is low compared to a hardware startup, especially in the quantum technology domain. So this is one limitation. And then second is in terms of funding. So usually any hardware startup, if you want to start, is going to need a lot of funding. And like you also mentioned about this, so Anuj also mentioned about this government fundings. And I think here government fundings are going to be really crucial because let's be honest, this is not a profit-making business, at least not in the coming years. So you will be developing technologies, but mostly for research. So it's not like commercial companies are going to benefit a lot from this. And this is where government should be funding. a lot in order to bear the cost. So it will be part of their investment, but towards such startups that are doing hardware research. And so this is one aspect. And second is what, so Devika was talking about these social stigmas. There's another social stigma involved with regards to quantum technology in itself. So people are usually both excited and scared by the word quantum. So the excitement comes from the thing that it is exotic, but that also creates a fear that, oh my God, you need to be some genius or you need to have some extraordinary skills in order to research in this area. And that needs to be broken, because if you look at the history of quantum, in most of the universities, the quantum research was actually happening in departments, let's say material science or electrical and electronics, mathematics in terms of theory and physics. So from here, the research already started. And even today, in the hardware of quantum, a lot of limitations and challenges are coming from the classical side. So because no matter how quantum your system is, ultimate control and readout is always electrical. It's always classical. And in that direction, so we, even in our university, we have a lot of engineers who are just engineers, not physicists. They are not, they do not know anything about quantum, and they're just helping us build the stack, or they're helping us avoid crosstalks in our circuit. Because especially when it comes to RF, there is a lot of physics, classical physics involved, that is extremely difficult to understand as a physicist or as someone who do not have a good RF background. And it affects your system a lot, even though it has nothing to do with physics. And this is why we need a lot of these cross collaborations. And finally, last point I want to make is with regards to industries. So again, coming to this cross collaboration part, industries have a lot of expertise when it comes to microwave technology, and RF circuits, and especially, readout equipment. So Keysight is one of the famous companies internationally speaking when it comes to RF tools. I don't know if we have such equivalent in India, at least I have not heard of, but building such a company should be easy, because in India we have a lot of electronics expertise, but not geared towards quantum. It's geared towards cell phone industry and communication industry, but it should also be geared towards quantum. And then what we can also think about, if this the progresses, is industrial PhDs. So you can have PhDs that are not just stuck in, like, I should not use the word stuck, but limited to academia, but also broadens the horizon with industries. And that can give a lot of cross collaboration, a lot of back and forth with the knowledge transfer, and it can be really enriching. So yeah. That's all.
So I'll throw few figures actually, just to, I think, soothe you a little bit. Okay, so one is in terms of actually funding. Okay, and it is a yearly based funding I'm talking about. Okay, the DOT plus DST plus certain other research organization, they have a funding of 700 crore per year for quantum technologies. Okay, going forward from this year onward, there's 700 crores. And they have invited not only, as I mentioned, the research organization from the government-sponsored like academia or anything, but also the private players. And that includes an international player. So I think Rajiv was mentioning about the Swiss part. So just to make you aware, I will like ID Quantic is one of that particular player who is actually working on the QKD in South Korea also. And they were one of the first, I think you might have heard of Samsung Galaxy Quantum mobile, which actually has a QRNG chip inbuilt. And that is the same thing which India would also be exploring. To be specific, CDOT will be working with ID Quantic, and there's an organization which is partner of ID Quantic. It's called SK Telecom, and it is a Korean organization. They would be working with CDOT, and they will be miniaturizing QRNG chip. And the other thing is also for the QKD also, there will be miniaturizing actually done. It is already a work in progress where QNU Labs is actually working. Okay, so there is, when you talk about the funding part, I think now with this Nirbhar actually Bharat and Make in India initiative, which is there, you would see the difference, and the difference is actually visible if you talk about the defense exports. Okay, that is one of the first step. And same thing will be happening in the other fields. So it should not, that is there. The problem is, which I think though India is not, I cannot compare it to the other ecosystem, but the thing is which should be taken care by the startups is that don't only rely on government fundings. Okay, have their own channels also opened where you can collaborate with, and this complete, you mentioned about the software stack and all those things, how the works are actually happening, like Classic, the Israeli organization, which is actually there. So they are working with other organizations to come. They don't have any hardware. Same thing I was listening to last evening, there was a discussion about Sandbox AQ. So they are not into hardware. Okay, so they only, I think they ship, if I'm not wrong, some tensor processing unit. Okay, but they are working with IBM and some similar organization to work in a ecosystem, and that is where all these costs get distributed. So there is a collaborator, like some organization might be having their own solution, and there is another one who would be contributing to their a bigger organization. And if I talk about the key insight, actually technology, because I have also interacted with them quite a lot in India. So they are already, first of all, their presence is very much in India, and they work in tandem with, you might be aware of, there is a organization, a government organization, Bharat Electronics Limited. Okay, so they are working with those sort of organization. As I mentioned, there are some confidential projects I cannot discuss about them, but they are actually working, and there are many such actually electronic based actually setups which are there in India, which are already working into cryogenics and control systems, everything.
Which is great for anybody that's looking into quantum from another technology perspective. I think we have to wrap up now because we've been going for 2 hours, and really appreciate that you guys signed up to do this, and we had such an insightful conversation. If you have any closing remarks, Devika and Rajiv, can just quickly, if you have anything to say, and then just like to say thank you, and we can close the meeting for today.
I don't have anything to add, but I did learn a lot during this session. So thank you for it. Thank you, everybody. Thank you, Priya, a lot, and also all the panelists. It was really nice. Thank you.
Yes, just to echo that, thank you so much, Priya, for organizing the panelists, and thank you, everybody, for attending.
Yeah. Thank you so much, everybody. This session is recorded, so if you want to catch it, we will eventually post it. And Achintya and Devika and Rajiv as well, thank you so much for keeping an eye on the chat and answering the questions on there. But that's about it. I hope we can have these sessions more often. This was great. This was insights from everywhere. Thanks, Anuj, for grounding us all and giving us the India context too. Yep. So thank you, everybody. Wherever you are, good night, good evening, good morning. Have a good day.
Bye.
See you then. Bye.
Yes. Thanks a lot, everyone. Bye-bye.
Thank you. Bye.